You made it sound like
she wasn't even in the car, and just like rolled back and hit mine. Because as they got out there, they just I literally ran out there. I didn't want her to try and fly away. So I appreciate that. Yeah. It doesn't look that bad now, it just looks like paint damage, but it's still really warm. What? It doesn't look that bad, actually. No.
I thought it was pretty bad.
In the picture, it really does look bad, but
You can bend your bumper out. Something you want. You want?
I know, but this is the problem that you gave us as extra credit. Remember, I got 4.5 points out of 5 on it.
Yeah. Right, I remember that. Was that for, okay, I'll have to, let me think about it here, what I did with, let me think about what I did with that, all right, but, yeah. Here is, okay. Okay. All right. Okay, let me switch gears here. Let's see. Oh, wait a minute. I've got a couple more tests here to distribute. Glad to see you. Okay. So the final is on Monday, and so we're going to take it at 11. I don't know. Brian, do you know offhand when you guys are going to be taking it? You're allowed 2 hours.
Okay. So it'll probably just be during the third and fourth hour. So like when Wednesday walks.
Okay, so like 10 to 12 or something? Mm-hmm. Okay. And we'll be taking from 11 to 1 here, right? 11 to 1. So whenever, it doesn't matter, just 2 hour block, whatever. I'll be online. You can tell them that I'll be online here starting at about 11 o'clock. So there'll be an intersection there if you guys have something you need to type in. All right, so just spread the word there. Spread the word here. I will an email. But this is one of the 2 documents that will be attached to the back of your final. This is that thing, if you remember this, that I had put up on the projector for the test one, all right, and you guys had available in the high schools also. Just these various antiderivatives giving you the sine inverse, the tan inverse, the sinh inverse, cosh inverse, those types of things. And of course, this can work in reverse then. Using the chain rule, you can then take the derivative and get things of this to get that, all right, going in the reverse direction. The other thing that you'll have available to you is that power series handout. So that'll be, those are the two documents that you'll have. All right. All right. So what I want to do actually today, and again, it's all going to be based on the problems from the 4 tests. The solutions are posted, and the only thing that I'll change on some of the problems is I'll just change the numbers. It could be the limit of integration. It could be some other number inside the problem that doesn't essentially change the type of problem it is. It just changes the number within the problem. All right. So I've got all the tests here. So let's start with test 1, and I'll go over a few things from test 1. That's what we're going to do today. And if you guys have any particular questions you want to bring up, then fine. So with test 1, test 1 was a lot about doing certain derivatives and integrals. So let's just look here at number 3A on test 1, where we have y equals the 4th root of the arctan of x, and you're asked to get the derivative. Well, for one thing, in case you're drawing a complete blank on the derivative of the arctan, you can utilize the handout here and see here we have the arctan. Its derivative of the arctan of x is 1 over 1 plus x squared. Okay, so you can get that right from that handout. So, however, here we have it's raised to the 1/4 power. So basically, it's arctan of x in parentheses raised to the 1/4 power. So we have to use the chain rule. So we have to bring down our exponent of 1/4, and we keep our arctan of x in here, lower the exponent by 1, which gives us, what, a negative 3/4? And then using the chain rule, we finalize it with taking the derivative of the arctan of x, which is 1 over 1 plus x squared. All right? And we're done with the problem. Similarly, we have, say, something right after that. Let's just look at part B here. We have y is equal to the arc sine of 5x, all right, and we want to get its derivative. Well, again, we can look here and see where we have the sine inverse right here, the second one. Its derivative of the sine inverse of x is 1 over the square root of 1 minus x squared. So we're going to use the chain rule here, and it's going to be 1 over the square root of 1 minus, now it's not just going to be x squared, it's going to be what? 25x squared. We take that 5x and we square it, so we're going to have 25x squared there. Okay, we're still not finished with the problem. We still have to use the chain rule to multiply by the derivative of 5x, which is 5, and then we're finished with the problem, right? Let's look at, say, if you have the test, or most of you don't, this would be number 4C from that test. And we have now we have an antiderivative of 1 over x times 1 plus the ln of x that's 1 plus, let me rewrite it. Antiderivative of 1 over x times 1 plus and then the ln of x is squared, and then another parenthesis, dx. So how would we go about tackling this?
The u equals ln of x.
Yeah, use substitution, u equal the ln of x. So we do a u sub ln of x, and of course the du that we get is 1 over the x dx. And if we look at our integral, we certainly have 1 over x dx right there in our integral. So this thing translates to this, where we replace the 1 over x dx with just a du out on the left, and then over here we have 1 over 1 plus u squared, all right? And then we're drawing a blank. We go and look here, and we see that the antiderivative of 1 over 1 plus x squared is the tan inverse, all right? So therefore this is going to be the tan inverse of the u plus a c, and then we back substitute our u. So this is the tan inverse of the ln of x plus our c, right? And let's see here. Let's look at the one right under it, 4D. And here we have the antiderivative of 1 over the square root of 16x squared plus 1 dx. Now, this is actually a form of one of the antiderivatives we have here. If you look at this list here, right here, we have the square root of 1 plus x squared, all right? So that gives us the antiderivative of the sinh inverse of x. So that's what we're going to want to use as our general template. But let's see here, we have to do some kind of u substitution, though, to get it like that. So we want to get it in the form 1 over the square root of 1 plus u squared. So what do I want to set my u equal to here? If I want to have it 1 plus u squared inside the radical, right, I want to see, well, 16 is a perfect square, x squared is a perfect square. So I set the u equal to 4x, u squared is going to be 16x squared. So I now need to get du, and that's equal to 4 times dx. So when I divide by, so if I want to just isolate the dx, I get that dx can be replaced by 1/4 times du. So using my substitution here, what I end up getting then, I'm going to replace dx with 1/4 du, and then I'm going to have for the rest of it 1 over the square root of 1 plus the u squared. So I've got it all substituted, and then I use my formula here, and my antiderivative is going to be the sinh inverse, okay? So this is going to be, I keep my 1/4, and then it's going to be sinh inverse of u plus c, but I replace my u then to get 1/4 sinh inverse of 4x plus c as my antiderivative. Okay. Right. Let's look at, on number 6, let's look at A and B here on number 6. This involves L'Hopital's rule. And 6a is finding this limit as x goes to pi of the sine of 3x over x squared minus pi squared. If we plug in the pi into both top and bottom, we get the sine of 3 pi on top, which is a 0, and then in the denominator we have pi squared minus pi squared, which is a 0. So this is that 0 over 0 case where I can apply the rule. So I take the derivative of top and bottom and do the same limit. So it's going to equal the limit as x goes to pi. The derivative of the sine of 3x is going to be 3 cosine of 3x, right? Using the chain rule. And then the derivative of the denominator will just be 2x, right? The minus pi squared will disappear. Now let's see what we have here. So now we have 2 pi when we plug in on the bottom, and then we have the cosine of 3 pi on top. So we no longer have the 0 over 0. We can just apply our limits. So this is going to be 3 cosine of 3 pi divided by 2 times pi. And what's the cosine of 3 pi? Negative 1. So this is negative 3, negative 1 times 3 over 2 pi. Okay. Let's look at the one right below it, 6b. And here we have to do a little bit of work. Again, we have the limit as x goes to pi, but now we have pi minus x times the tangent of x over 2. All right. So now we don't have something divided by something. We have a product of two things. Now, if we plug in our limit value, pi minus x then becomes pi minus pi 0. And then plug in the pi here. We have tangent of pi over 2. Now, what's the tangent of pi over 2? Infinity, right? It goes up, keeps getting bigger and bigger because it's sine over the cosine. Cosine goes to 0. So this is the 0 times infinity case. So we can apply the rule here. Now, basically, we want to convert this into either an infinity over infinity case or a 0 over 0 case. Okay? And generally, there is an easy way to do this and a hard way to do this, all right? So we want to pick the right, moving the right thing into the denominator so that we make it easy for ourselves. So what I want to then do is re-express this product as a quotient without changing what it is. So what do you think we might want to try initially and hope for the best and see how that turns out? Which one do you think we want to move? The tangent I think is going to work out best when we move it. So I want to keep the pi minus x here in the numerator, and then I want to move the tangent down in the denominator. So what does the tangent become when I move it into the denominator? Right. It becomes the reciprocal, which is the cotangent of pi over 2. Now what do we have? What kind of case now do we have? Now we have pi minus pi, so we have a 0 on top. And this should be an x over 2, sorry. Cotangent of x over 2. And the cotangent of pi over 2, cotangent is the cosine over the sine. Cosine would be 0, sine would be 1, so that's also 0. So we have a 0 over 0 case. So we can apply the rule. So this is going to be the limit as x goes to pi of the derivatives of the top and bottom. Derivative of the numerator, the pi is going to go to 0, is just going to be a -1. Now, the derivative of the cotangent, let's see, derivative of the tangent is the tan c, derivative of the cotangent is the minus cotangent cosecant. So, wait a minute, no, derivative of the the derivative of the tangent is the secant squared. And so the derivative of the cotangent is the minus cosecant squared. And that's applied to pi over 2. Okay. Well, actually, I'm plugging, yeah, you're right, x over 2, right. And then I apply my limit value. That's where I was jumping ahead. So I have -1 on top, and I have minus cosecant squared of pi over 2 on the bottom. Oh yeah, right, exactly. So I need a 1/2 also. Yep. Okay. So we have minus 1/2 times the cosecant of x over 2. All right, so what are we going to have here? What's the cosecant of 90 degrees?
1.
Yeah, because cosecant is the opposite of the, cosecant is going to be, is the opposite reciprocal of the sine, right? And the sine of pi over 2 is 1. So this is, yes, this is 1. So we have -1 over minus 1/2, which simplifies to the number 2. Okay. All right. Okay, so that's that rule there. So this is the type of thing then that you'd have from test 1. Right. Okay, then let's go to test 2 here and see what we come up with here. Now, test 2 was all of those techniques of integration, where we had integration by parts, trig substitution, simplifying trigonometric integrals, and so let's see what we can have here. Let's look at, first of all, some integration by parts. How about this one? This is number 1B. Remember, on this test, I had an A and a B problem for all of the questions. So this is evaluating the integral of the arc sine of x dx. Okay. So this can be done using integration by parts. Okay, so we have, remember, integration by parts is the integral of u dv equals u times v minus the integral of v du, right? So we want to be smart in the way we choose u and in the way we choose dv here. All right. Any recommendations as to what we might want to pick then? We don't have a whole lot of stuff to choose from. What we want to pick is u and what we want to pick is dv in that integral. Yeah, if we do u equal arc sine, we'll come out ahead here. So let u equal the arc sine. And remember here from the handout then that here it is. The derivative of the arc sine is 1 over 1 minus x, square root of 1 minus x squared. So therefore, if we let u equal this, the du then is going to become 1 over the square root of 1 minus x squared dx. And that's going to work out further on. Now, if u is equal to the arc sine, the only thing we have left then is dx. And so the dx has to equal the dv. And when we integrate both sides of that, we end up with our v then equals x. All right, so we have all the parts that we need here in order to now put this together. So u times v is going to be x times arc sine of x, that's u times d, minus, and then v du is going to be x, and then du is this 1 over the square root of 1 minus x squared dx. So this ends up working out because what can we do to evaluate that second integral there? A u substitution. So what, Nikisha, what are we going to have u equal then? Right, let u equal 1 minus x squared and it'll work out. Du then is minus 2x dx. We already have the x dx very nicely, so if I just divide by -2, so negative 1/2 du is going to replace my x dx. Right? All right, so let's see what we get here. So we get minus the integral of minus 1/2, and then it's 1 over the square root of u. So to get the antiderivative, I might want to rewrite that with exponents, and that's going to be u to the negative 1/2 power, and so therefore, and then du. All right. Okay. So this is going to simplify then. I'm going to have a double negative. That's going to be plus 1/2, and then this is going to be u to the 1/2 times 2, or divided by 1/2 for my antiderivative. So that simplifies, of course, to u to the 1/2 power, which, going back up here, is going to be the square root of 1 minus x squared. So what I finally come up with then is this. uv is x times arc sine of x. I had a double negative, so I have a plus the square root of 1 minus x squared plus my general constant. So the trick is finding out the right u to do. Let me do one more integration by parts here. How about 2b in that test? And this one is antiderivative of x, e to the minus 4x dx. All right. So hopefully we can see, I hope we can see what would we want to use as the u here. X. Yeah, because we want to get rid of that. So let u be equal to that x, and then du is just going to become dx. The rest of this then is my dv. This is u dv. So dv then is the rest of this, which is e to the minus 4x dx. And I then need to get the antiderivative to get v. And what's the antiderivative then, without having to mess with all kinds of u substitutions, of e to the minus 4x? Right. You just take that number that you've got there, multiplying the x, that just gets flipped in the denominator. So it's 1 over minus 4, which would be minus 1/4, and then e to the minus 4x. There were a couple of, I think they were on the test that I graded, there were a couple of people that wanted to do, for the e function here, wanted to raise the exponent by 1 and divide by the same. You never alter the exponent of the e function when you're doing either derivatives or antiderivatives. So you never do that, where you would say this would be minus 4x plus 1. And I put a big, on the test, I put a big no next to that you don't do that. So this is the antiderivative And so that gives me my V. So now I have, let's see, U du, I have dV, I have all of my parts here. So therefore, this is going to be uv minus v du. So u times v is going to be minus 1/4 times x, e to the minus 4x, that's uv, minus, now v is, again, you got to watch out, often we have double minuses, minus 1/4 e to the minus 4x, and then that's our v, and our du, notice, is just dx. Okay. All right, so again, we have a double minus, that's going to turn into a plus, and then again, we do that same business here, getting that antiderivative. We put that minus 4 in the denominator, so that's going to give us 1/4 times negative 4, so that's going to give us a negative again, minus 1/16. And then e to the minus 4x. So basically then, our answer is minus 1/4 x e to the minus 4x. I'm sorry, this should be a minus. I've got a minus 1/16 e to the minus 4x plus c. Okay. All right. The next thing in this section had to do with integrals that contain trig functions in them, either sine and cosine, or secant and tangent, cosecant and cotangent. And we had to do some manipulation here and use substitutions. So let's look at a couple of these. We'll just look at ones involving cosine. This is 3a, and I'll also do 3b. So 3a is this, find the antiderivative, or find the value of this definite integral from 0 to pi over 2 of cosine to the third of x times the sine of x dx, all right? Now this one, there's actually a pretty easy way to do this without having to use any trig identities. Anybody have an idea on how I might approach this one to get the antiderivative? Right. Have u equal the cosine of x. The derivative of the cosine is the negative sine, which I almost have up there. I have sine. So I can just, in this case, I can just use the simple u substitution and solve it. So let u equal the cosine of x. Du then is going to be minus the sine of x dx. So I'm going to replace, if I multiply both sides by -1, I can replace sine of x dx with minus du. So this thing becomes then cosine cubed will be u cubed. Sine of x dx I'm going to replace with negative du. All right. Now, what do I need to do about these limits of integration when I do a u substitution? Do I just keep them the same, or do I do something with them?
Change them.
Yeah. Unless I choose to go back to cosine again, which is the hard way, if I just want to keep the u here, I need to change the limits of integration. So we know here we have x equals 0. So I plug in, so u is equal to the cosine of x. So the corresponding u is going to be the cosine of 0, and that's equal to 1. So my lower limit is going to be the number 1. Now my upper limit here is when x is equal to pi over 2. I then have u, my corresponding u is going to be the cosine of pi over 2, and that's a 0. So it's weird, but my upper limit of integration is a 0, and we can have that as long as we just follow the rules. Now I could switch this around, take out the minus, and then flip the limits of integration, all right? Everybody understand that? But I can just keep it like this as long as I watch out for minus signs. So my antiderivative of minus u to the third is minus u to the fourth over 4, right? And my upper is 1, my upper is 0, my lower limit is 1. All right. So when I plug in the upper limit, of course I get a 0. Now here's where you do have to watch out then for double minus signs. I then minus, and I plug in my 1, which is going to give me now a minus 1/4. So I have to then change the double minus to a positive, and my answer becomes 1/4. Right. Okay. Let's look at the one next to it, 3b. Another definite integral, 0 to pi over 2. And this time it's 2 times the cosine squared of x over 2 dx. So there's this formula that you certainly had to use on the last test, and I think you also had to use it on this exam too, of course, and you won't be given this formula, so let's try to remember this, that the cosine squared of alpha is 1/2 1 plus the cosine of double alpha, 2 alpha. And then there's a corresponding one for the sine squared. But sine squared is 1/2 times 1 minus the cosine of the 2 alpha. All right. So both of those you need to be remembering. So we can therefore replace cosine squared here using this formula, right? We don't have to do a u substitution. So I have u to 0 to pi over 2 of 2 times, okay, cosine squared of x over 2. It's going to be 1/2 times 1 plus the cosine. Now what am I going to be replacing this with now? Right. This, I'm going to replace it with x. This angle here is twice this angle. So if this original angle is x over 2, twice that is the angle x. Close my parentheses, my bracket, and dx, and now I come up with a easy antiderivative to get. Let's just multiply things out. 2 times 1/2, that's just going to cancel out in this case. So I just have 1 plus the cosine of x. Get the antiderivative, I have x. Antiderivative of the cosine is the sine of x, and then 0 to pi over 2. So that's going to basically come out to pi over 2 plus 1, and then the two terms that I subtract off are both 0. So that would be my answer. All right. Now, the next thing from this test were, let's look at 5A. These were ones where you use a trig substitution to solve it. So use a trig substitution. So what do we have here? We have the integral from 2 to 4 of the square root of x squared minus 4 all over x dx. And we're going to use a trig substitution to solve this. So does anybody remember when we have the x squared leading minus this, what trig function we would use as our substitution? The secant, right. Okay? The secant, remember, the secant is always bigger than or equal to 1. So we're going to use the secant. If this were 4 minus x squared, we would probably use what? Yeah, we would use the sign, but it's x squared minus the 4, so we're going to use the secant. So is it just plain secant? So we're going to let x equal, we're going to have the secant of theta, but what else do we need to put here? We have a minus 4. To make this work out, I have to put what in front of it? A 2, yeah, the square root of that. And then it'll work out. So let x equal 2 times the secant. So we know to use the secant because we're leading with the x here, and then the 2 comes from the square root of that other number. So now we get our dx, and our dx is 2 times, okay, the secant is the secant, that's the tangent. So dx is 2 times the sectangent d theta. All right. And let's see what the radical is going to be replaced by. X squared then is going to be 4 times the secant squared of theta, when we square it, minus 4. So that's going to be what? We can take out a 4 here, so that's going to be a 2 on the outside. Nice perfect square. And we're left with the square root of secant squared of theta minus 1 under the radical. So trig formulas that you need to remember is we know that the sine squared of alpha plus the cosine squared of alpha equals 1. Well, the corresponding ones using that Pythagorean theorem are this. 1 plus the tangent squared of alpha is equal to the secant squared of alpha, or 1 plus the cotangent squared of alpha is equal to the cosecant squared of alpha. Those are all based on the Pythagorean theorem. So I can replace secant squared minus 1 with the tangent squared right here. So this is 2 times the square root of the tangent squared, all right? And where we're talking about here, we're going to be, I think we're just going to be dealing with the first quadrant, so we're going to have a positive tangent. So we can replace the square root of the tangent squared with just the tangent. So that whole radical then becomes 2 times the tangent of theta. All right. What about my limits of integration here? I've got a 2 and a 4. What are those going to be replaced by? Well, let's see. When x is equal to 2, what are we going to have here? 2 is going to be equal to 2 times the secant of theta. Oops. 2 is equal to 2 times the secant of theta. So the secant of theta is equal to 1. And that occurs at what angle? 2 pi, or how about just 0 also? Because the secant is 1 over the cosine. So just 0, because this is our lower level, lower limit, why don't we just make it a 0? So theta is equal to 0 degrees, all right? And then for the upper one, now we have a 4, so x is equal to 4. So we have 4 equals 2 times the secant of theta, which means that when I divide by 2, that means that the secant of theta has to equal the number 2. So that's going to be the 30, 60, 90 triangle, right? So let's see. What angle has a cosine of 1/2? Pi over 3, right. So therefore, the secant of 60 degrees, or the secant of pi over 3, if we look at this, pi over 3, pi over 6, 1, square root of 3, and 2, we see that the secant of pi over 3 is 2. So therefore, our upper theta is going to be pi over 3. Okay, so let's do our substitution here. Our bottom limit is going to be 0 degrees. Our top limit now is pi over 3. And let's do the replacement. Okay, the radical got replaced by 2 tangent of theta. The x here gets replaced by 2 secant of theta, tan theta, d theta. And then we also have an x down below. That x is going to be replaced by 2 times the secant of theta, right? So we can cancel out a few things. Cancel out a 2, cancel out a secant. So what we're left with then is 2 times the tangent squared. 0 to pi over 3, 2 times the tangent squared of theta d theta. Okay. So how do we then go about getting this antiderivative of the tangent squared? Yeah, okay. We want to get this because we know that the derivative of the tangent is the secant squared. So we want to get the secant squared involved with this. So we go up here, just remember our Pythagorean formulas up here, and the tangent squared can be replaced by secant squared minus 1. So we're going to do that. So this then gives us 0 to pi over 3, 2, then parentheses, secant squared of theta minus 1. And now we can get the antiderivative of this. This, of course, distributes as 2 times the secant of theta minus 2. And we're on test number 2. We're looking at 5A. If you want to see these things afterwards, that's fine. Okay. So let's get the antiderivative then of each of these things. The antiderivative of 2 times the secant squared is going to be 2 tangent. Derivative of tangent is secant squared, so that's going to be 2 tangent of theta. And just the derivative of minus 2 is going to be minus 2 theta. And then we apply our limits. Okay. All right. So we have 2 tan of pi over 3 minus 2 times pi over 3. And the bottom limits in this case are both going to be 0. Tan of 0 is 0, and theta is going to be 0. So we just need to figure out tan of 60 degrees, and the tan of 60 degrees, go up right here, is square root of 3. So this is 2 times the square root of 3 minus 2/3 pi, and we're finished with this problem. So the thing is, remember when to use the secant, when to use the sine. If this were the square root of x squared plus 4, what would I use? Tangent. And it would be 2 times the tangent. When you have a plus, you would use the tangent. Okay. All right, so trig substitution. Our good friend partial fractions may be rearing its ugly head, but these aren't so bad. They can be bad, but they can also not be so bad. This is 6, let's look at 6a. And here we have, we're trying to find the antiderivative of dx over x times x minus 1 squared. All right. I'm going to use partial fraction. So I need to take this integrand and expand it into individual fractions. My denominator, first of all, I'm going to have my x here, and I'll put an a over that. Then notice this x minus 1 is squared. So I need to have one term which is just the x minus 1 with a b over that. And then I also need a second term which has the square, the highest power of the x minus 1. And again, I'll just have a c over that one. All right. And then we basically multiply both sides by this least common denominator, and we're going to get some equations here. So I'm to multiply everything by x times x minus 1 squared. So the left is just going to be a 1. The first term here, the x's cancel out, but I'm still left with an x minus 1 squared. For my second term, one of the x minus 1's cancel out, but I still have an x and an x minus 1. And for my third term, both of the x minus 1's cancel out, but I still have an x. So I have that. And then there's a nice quick way to at least get a couple of these coefficients, and what would that be?
Plug in 1.
Okay, plug in 1, and I will do that. What's another number I can plug in? 0 would be the other one. Because this has to be true for all values of x. So let's plug in x equals 1. So I get 1 equals, that's going to be 0, 0, c times 1. So we know that c has to equal 1. Let's plug in 0. So we have 1 equals, okay, when I plug in 0 here, I'm going to have minus 1 squared. So that's going to be a times 1. And for the next two terms, when I plug in 0, they both become 0. So I have a is equal to 1. All right. The only one I need to do some work on is b. All right. Now, I could use another value of x in order to try to find out what b is. All right. That's one possibility. Another one is to realize that this term expands as a times x squared plus some lower powers of x. This one distributes as b times x squared minus b times x. So the only two terms that have x squared on the right-hand side have coefficients a plus b. So a plus b times x squared from the right has to be 0 because I don't have any x squares on the other side. So therefore a plus b has to equal 0. So therefore b is the opposite minus a. So therefore a is 1. We know that b is negative 1. And that's the main work that we have to do. The rest of it is downhill from here. We then just rewrite our integral with these a, b, and c. So a is 1, so it's 1 over x. b is minus 1, so it's minus 1 over x minus 1. And c is 1, so it's 1 over x minus 1 squared dx. So I end up with 3 terms, all of which I can get the antiderivatives of. Okay? So we do them one at a time. First term is going to be the natural log. Without having to do any kind of fancy u substitution, what's my second one going to be? Yeah, minus the ln, I got a minus here I got to keep in account, of just the absolute value of x minus 1. You do a u substitution, you're going to end up with that same thing. Now this one I just have to then do my power rule. This is really x minus 1 raised to the negative 2 power. So remember, we add 1 to the exponent and divide by the same. So therefore, this is going to be x minus 1 raised to the negative 1 power. And then we have to divide by negative 1 plus c. And then, so I can rewrite this as ln. If I want to really look good here, I can combine those two natural logs into a single one. And then minus 1 over x minus 1 plus c. Right? All right. And that's it for test 2 then. I want to look at it. Why don't we take a couple-minute break? Brian, what I'm going to do on Monday is I'll be dropping by, which is what I was going to do today, but your schools are closed. I'm going to go by the Welcome Center on my way here. So I'll drop off your test early, like at 7:30. All right. So Delmeyer is supposed to know, he knows that.
Yeah.
So you guys will have an opportunity to at least, I'm going to tell them in an email, just give you an opportunity to at least look over your test for a few minutes before you then take the final.
All right, I've got a couple classes that senior now. I can skip whatever I see.
Mm-hmm.
Yeah.
Are any of you guys signing up for next semester?
Yeah, I am. My dad is my social security number.
Okay.
And I think there's only one student not taking, and that's Sam.
Oh yeah, he said. Yeah, I tried to coerce him into it, but he apparently is not buying it.
Yeah, Sam.
Yeah, right.
It's okay then.
Yeah. Yeah, it depends on what you need, and certainly not everybody needs 3 semesters of calculus, right?
For 3A. What kind of series is that?
For 3A. Okay, that's a geometric series. Yeah. Basically, yeah, so if you kind of simplify things a little bit, you've got the summation 3 to the n over 2 to the 2n as n goes to 0 to infinity. Well, we can kind of fiddle with this a little bit. Notice both of these are raised to the nth power. So we could rewrite this as 3 over 2 squared, close parentheses, and all of that's being raised to the nth power, right? And then, of course, that's 3 over 4, all raised to the nth power. So we have a geometric series right there with 3 over, or r then is equal to 3 over 4. So therefore, because that's less than 1, the next question is, it'll be convergent then. Yeah, right. And then you can compute the limit. The limit is a over 1 minus r, where a is the first term. So the first term of this, you have to be careful with this. The first term of this is n to the 0, n is 0 power. So the first term is really a 1 here in this series. So if you're computing the sum, the a is 1 minus 1 over 1 minus 3/4, and then you compute that, and you get a 4. All right. Okay. What I want to look at here then on test 3, if you remember there was a whole series of fill-in-the-blank questions from test 3. Do we remember that? No, we don't remember. Yes, we do. All right, so here, let's look at some of these here. This is number 1 from test 3, all right? And so, first thing we're told, if the limit of a sub n is equal to 2.7, then the sequence a sub n is what? Is blank. Not a series where we're adding things up, just a sequence. And the limit is equal to 2.7. Yeah. Be nice. Convergent, right. It's convergent. It has a limit. If the limit of a sequence is a finite number, it doesn't have to be a number less than 1. Any number, any finite number, is a convergent sequence. All right? The next thing then, if we have a p-series, remember that's where we have the sum of 1 over n to the p power, and that's n equals, say, 1 to infinity. So the p stays the same. And basically, if the question here is this, if p is bigger than 1, this is what? This p-series is what? In other words, if it were something like the summation of 1 over n squared, is that a convergent series or what? It's convergent. When the exponent there is bigger than 1, it's a convergent p-series. Okay? If p were less than 1 or equal to 1, say the sum of 1 over n, that's divergent. Even though you'd think it looks like it's convergent, this is a divergent p-series if p is less than or equal to 1. What about if we have a series, let's just denote the series as the sum of 1 of a to the n as n goes from 0 to infinity. And let's say that it basically, the terms have different, or I could put it this way, the terms don't all have the same sign. In other words, some terms may be positive and other terms are negative. So the terms don't have the same sign, but the summation converges. So you find out the summation does converge, okay? But if I do the absolute value of all of the individual terms, and I'm summing that up, that absolute value diverges, then there's a term to describe this series. Then the series is blank, blankety blank, blank, blank. Conditionally convergent. Right. The series in and of itself does converge, but when we do absolute values on each of the terms, because some are positive, some are negative, then it goes to infinity. The series is conditionally convergent. Okay. What about this? If the limit of a sub n is equal to 1/3, then the summation of the a sub n's is what? So we're talking about the individual term, those limits go to 1/3. But now we're talking about summing with a series. What can we say about the series? If these things tend to go to 1/3, and I'm summing them all up. Well, think about, what if you were taking the number 1/3 and summed it and summed it and summed it and summed it infinite number of times? Would you come up with a finite number if you kept summing the fraction 1/3 and 1/3 and 1/3? No. Thank you. No, you wouldn't. So what do we think might be the answer to this then?
Divergent.
It does diverge. Right. Right. The only way, when we have a series, we have this fact here. Fact. If the series, and with the series we're always talking about summing. If the summation, if this series is convergent, does go to a finite number, then the limits of the individual terms has to equal a 0. All right? So I kept trying to repeat that and repeat that before we got to this test 3. But, so this is a fact. So that's why if the limit is 1/3, it has to be divergent. However, what about what about this statement? Let me flip this around. If the limit of a sub n is equal to 0, then the summation of the terms is convergent. Can I flip that around like that and have a true statement? Okay. All right. So Jordan at least went out on a limb and gave me an answer. Thank you. And he said the answer is no. This is not necessarily a true statement. And all you need in mathematics is a single example to show that something is false. All right? Look at the series, the summation of 1/n as n goes from 1 to infinity. All right? This is called the harmonic series, and we know that this is divergent. But this is our a sub n here, 1/n. What's the limit of 1/n as n goes to infinity?
0.
It's 0, right? N denominator keeps getting bigger and bigger. So we can have a divergent series, and yet the limit is still equal to 0 of the individual terms. But if the limit is equal to 0, if the series is convergent, then the limit has to equal 0. So what I want to lead up to is this statement here as part of these questions. If a series, so say the summation of a sub n, is blank, then the limit of, as n goes to infinity, of the a sub n's is equal to blank. And I want to fill this in to make it a true statement. And there's only one possible answer. Right. If the series is convergent, then the limit of the terms has to be 0. The other possible answer is false. You may want to say, well, I could have filled this in with if the series is divergent, then the limit of a sub n does not equal 0. I could have filled it in that way, and that would not be a correct statement, because we already went through an example of the summation of 1 over n. This is a divergent series, but its limit, its limit does equal 0. So there is only one possible answer here for this type of question. Okay. Let's just do a couple more with this one, and then we'll go on. Using the limit comparison test. What's that? If we know that the summation of a sub n is convergent, say it may be a convergent p-series or something like that. If we know it's convergent, and if the limit of b sub n over a sub n is equal to the number 3, then the summation of the b sub n is what? So basically we're looking at the summation of the b sub n is we're looking either for divergent or convergent as the two possible answers.
Convergent.
Okay. And why?
Because in comparison test, if it was a positive finite number, then they're both convergent.
Right. Right. In the limit comparison test, if we know that one of our series is, say, convergent, and as long as the ratio of the terms is a positive finite number, the other one is also going to be, if this one is convergent, then this one is going to be convergent. And it works with also divergent. If we knew that this one was divergent, and the ratio was a positive finite number, then the other one would also be divergent. That's the LCT. Yeah, Brian? It doesn't matter. It doesn't matter. It could be Bn over An. Because if I did An over Bn, it would just be 1/3. All right? Okay. In fact, I think actually we're talking here about, with the limit comparison test, we're talking here about, just as a side note, that the series only have positive numbers. Okay? So therefore, the a sub n's are bigger than 0, and the b sub n's are also greater than 0. It's a strictly positive series. This is the last one I'll do on this page. There's a lot of questions on this page, and I'll just look at this one. In the ratio test, so we have this ratio test. If we find out that the limit of a sub n plus 1 over a sub n, do the absolute value as n goes to infinity, if that is less than 1, then we can say that the summation of the a sub n is blank, blank. Okay. Absolutely convergent. If that limit of a sub n plus 1 over an to the absolute value is less than the 1, then the series is absolutely convergent. Okay. There are a lot of problems here in this section. Let's look at this one, in this test rather. Which one is this here? Let's look at number 8. And here we're given what's called a power series. Summation of n equals 0 to infinity. Power series have the variable x in them that keeps getting raised to a higher power. X minus 4 raised to the nth power over 3 to the n times n plus 3. So this is our what's called a power series. We can expand this out when n equals 0, n equals 1, and add them all together. What I just want to look at here is find the the radius of convergence. All right. All right. So when there was that strategy handout that you guys got before this test, when we have things like a constant raised to the nth power, what we usually want to use, remember we have various tests. I could use the root test. I could use the ratio test. It's best to use, when we have a number raised to a power, it's more effective to use the ratio test to figure this out, right? So we had just kind of written the ratio test. We look at the limit as n goes to infinity. Now, it's basically, it's a to the n plus 1 over a to the n, absolute value. So here, we're going to end up with initially what looks like a big mess, but it's going to simplify very nicely. First of all, up here for the numerator, we want to fill in n plus 1 for all the n's, and we put that in our numerator as our a sub n plus 1. So up here, I have x minus 4 raised to the n plus 1 over, instead of 3 to the n, I put 3 to the n plus 1. And then here, instead of n plus 3, I put n plus 1 plus 3, which is n plus 4. And then down here in the denominator, we put a to the n. So that's going to be x minus 4 to the n power over 3 to the n times n plus 3. So that looks like a real mess, but so we have a fraction divided by a fraction. So do we recall how we can simplify a fraction divided by a fraction? Yeah, multiply by the reciprocal of the denominator. So I've got x minus 4, I've got my numerator, x minus 4, n plus 1, 3 to the n plus 1 times n plus 4, that's my numerator. But now I'm going to multiply it by the reciprocal of the denominator. So that's going to be 3 to the n times n plus 3 all over x minus 4 to the n. And then things cancel out when I do this. Notice I have a 3 to the n and the 3 to the n plus 1 here. So that'll fully cancel out, and I'll be left with the 3 down there. Here I've got an x minus 4 to the n plus 1, x minus 4 to the n. This one will cancel out, and up here I'll just be left with a single x minus 4. So this is what I get. The limit as n goes to infinity of the absolute value. Okay, on top all I'm left with is x minus 4. And the denominator, I have a 3 that's left. Oh, I'm sorry. I forgot about that. And I also have an n plus 3 in parentheses in the numerator. Denominator, I have a 3. n plus 4 in parentheses, and we have that. Now, I want to find the radius of where this thing converges. So remember, for the ratio test, that's going to converge if this limit is strictly less than 1. So I take x minus 4. And also, wait a minute, what's this limit going to be as n goes to infinity? What's the limit of n plus 3 divided by that n plus 4 as n goes to infinity? It's just going to be 1. Because the trick, remember the trick, just divide by the highest power. This is 1 plus 3 over n in the numerator, 1 plus 4 over n in the denominator. These both go to 0 as n gets bigger, and all we're left with is a 1. So this is equal to 1. So when I do this limit, I'm just left with x minus 4 over 3 absolute value, and I want that to be less than the number 1. Okay, so then what do I do to figure out my radius of convergence? Yeah, multiply both sides by 3. So x minus 4 has to be less than the number 3. And the number 3 here is my radius of convergence. Okay. All right. I'll do one more from this test. Let's look at let's look at number 4. Okay. All right. So this one, we're again asking whether a series is convergent or not. And here's the series, starting with 3, n equals 3 to infinity of 1 over n times the square root of the ln of n. All right. And actually, on this series, you were told in the instructions to use the integral test. Okay. Okay, so with the integral test, then, I have to get a corresponding function, and I'm going to be taking getting the integral of it. So what would be my function that would correspond to 1 over n times the square root of ln of n?
Just replace the n's with x.
Yeah, right. Just replace the n's with those continuous x's, so 1 over x times the square root of the ln of x. All right. Now, to use the integral test, the function has to be positive in value, and this is always positive in value. The function has to be continuous. What is one other condition that the function must have for this test to apply? Well, no, we got that. Positive, it's continuous, it has to be decreasing. So the f of x must be decreasing, and I think without even doing any kind of derivative, you can see, I would hope that you can see with this, that as x gets bigger, the denominator gets bigger, and so the function gets smaller. All right, just basic eyeballing and seeing that it's a decreasing function. So we can use the integral test. So we just evaluate the integral. And in this case, we're evaluating it from 3 to infinity of dx. All right. And basically, we just want to find out, does this thing converge or diverge? And I don't think I'm going to go through this, but just want to go through this. To evaluate this integral, what technique do I use, and tell me what it would be. Right. And what would my u be? Right. Figure it out using u equal the ln of x, and what we're going to find out when we do this is that this is a divergent, this thing becomes, this integral equals infinity when we do our u substitution, so therefore this series here, because it equals infinity, this series is a divergent series. That's right. Okay. Then that leaves us with test 4, which I was a bit disappointed in. It was not a fun experience grading test 4. I will say that. And I think I blame some of that on just being the end of the semester. But let's see what we can do here with test 4. Because I found some people were getting, and I know there's several formulas with test 4, and some people were getting confused between arc length and versus surface area. I mean, that was a point of confusion for some folks. Let's look at number 2. This is on test 4. And here we're asked to find the surface area. It's rotated about the y-axis, or is it the x-axis? Yeah, it's the y-axis. And the function is y is equal to 1 minus x squared. And it's from 0 to 1 for the x. All right. Now, the thing is, with surface area, if it's rotated about the y-axis, first of all, the general formula is going to be 2 pi x ds, all right, for the y-axis. If it were rotated about the x-axis, it would be 2 pi y ds, right? Now, so this is about the y-axis, so it's going to have this type of format to it. Now, what's the ds going to be here? Well, in this case, ds, we're going to be using dy dx. Y is given as a function of x, so we're going to use dy dx. ds is 1 plus dy dx squared dx. There's all different kinds of formulas for ds depending on what you're given. This is the one if you're given y in terms of x. So let's figure out dy dx then is an easy derivative to get. That's minus 2x. So therefore ds then is going to be the square root of 1 plus the square of that dx, which is 1 plus 4x squared dx. So this is what we're going to have then. Our limits of integration are from 0 to 1, 2 pi x times the square root of 1 plus 4x squared dx. Right? And we can do a u substitution and get this. I won't go through the u substitution, but I'll just say this is the u sub we would use is let u equal 1 plus 4x squared. But I will say this, because this is something I found on a couple of papers. Okay, we're fine on doing the u sub, but what some people are not so fine on are changing the limits of integration. It's just being forgotten about. My limits of integration of x equals 0 to 1. If I'm replacing x with 1 plus 4x squared, I have to change my limits. So when x is equal to 0, u is going to be 1 plus 0, so u is going to be 1. If my x is equal to 1, then u is going to be 1 plus 4, 1 squared. U is going to be 5. So I do have to change my limits of integration along with doing the u substitution. Okay? Here's another one. Let's look at this one. Here's an arc length one, and it involves using a different formula for the ds. This is number 5. And it's find the arc length of the curve. Now the curve here is a parametric curve. It's x equals 1/2 t squared, y is equal to 1/3 t cubed, and our parameter is going from 0 to square root of 8. All right? Okay. All right. So the formula for arc length is going to be here. It's basically going to be that ds. But the ds here is going to be the square root of dx dt squared plus dy dt squared dt. Okay, that's how it has to be represented. All right. So basically, I don't want to say much more about doing this problem. We just have to, what we're going to end up with, dx dt is going to be t, and dy dt is going to be t squared when we do the derivative. So we have the square root of t squared, which is t squared. Derivative of square of t squared is t to the 4th, and we have that. And then again, our limits of integration are 0 to the square root of 8. You guys, so what did you guys do from there on this one? Yeah, pull the t out by pulling a t squared out of the radical. So we have a t being brought out, and what we're left with then is 1 plus t squared under the radical. All right. And again, we can do a nice u substitution where u is equal to 1 plus t squared. And again, as a reminder, the limits of integration then have to change accordingly. When t is 0, u is going to equal 1. When t is the square root of 8, u is going to be equal to 1 plus 8 or 9. Okay? And then we go on and finish the problem. I'll just set up this one so that we're clear on how this problem is set up. This is number 6. And I'm just going to set it up. Here we're finding the surface area again. And x is equal to e to the t minus t, y is equal to 4e to the t over 2. And again, we have a parametric curve. T is going from 0 to 1 again. And we're rotating this about the x-axis. So when we're rotating about the x-axis, the general formula then is 2 pi y ds. Now, the y here, first of all, let's figure out what the ds is going to be. Since it's a parameterized curve, we're going to use this formula for the ds. The square root of dx dt squared plus dy dt squared dt. So that's that. What am I going to use here? So that's what I'm going to use for my ds. What am I going to use for my y?
What y equals?
Yeah, what y equals 4e to the t over 2. Duh. Right. All right. Some people had algebra problems with what's under the radical. All right. So maybe I should just kind of go over this. dx dt is what? E to the t minus 1. dy dt is 4 times 1/2, 2 times e to the t over 2. Okay, when I square dx dt, I'm squaring e to the t minus 1. So that's e to the t times e to the t, that's e to the 2t minus 2e to the t plus 1. And then I'm adding, then when I square dy dt, I have 2e to the t over 2 squared, and that's going to be 2 squared is 4, but when I square e to the t over 2, I multiply the exponents, I get e to the t. So what I get under this radical then is the sum of these two, e to the 2t. When I combine these two together, I get 4 minus 2, I get 2e to the t, and then I have a plus 1. And this becomes a perfect square under the radical. This right here is e to the t plus 1 squared. So that whole radical simplifies to just e to the t plus 1 when I do the square root of that. One thing, one welcome relief, you won't, I don't have any, where you're actually graphs. I don't have any graphs on there. So hallelujah. Number 7, part C. This is where we have this function, this polar function, r equaling 4 cosine of 3 theta. And I must admit, I don't think it was so much in this class, but I had some extremely interesting looking graphs for some of these things. All right. Okay, and what are we asked for in 7C? We're asked for the area under one loop of this curve. Okay, when you graph it, it looks something like this, then we have another leaf there, we have another leaf there. Okay, that's what it looks like. And the whole purpose of this graphing, and this is where some people messed up, is to give those limits of integration there at the top and the bottom for, say, this first loop right here. That occurs where your r goes all the way back in and equals 0. When you set r equal to 0 up here, basically try to figure out what your theta is. Well, I divide by 4, I just get cosine of 3 theta is equal to 0. All right. So therefore, so what do we have here that a cosine is equal to 0 when? Well, it's equal to 0 at pi over 2, right? So therefore, that means 3 theta has to equal pi over 2, right? Because cosine of pi over 2 is equal to 0. So if I divide by 3, I find that theta equals pi over 6. And when you guys did this, most everybody was fine with filling in these items here. And notice that pi over 6, or r, yes, or r does equal 0. It folds in on itself. And the reason I started it up here at minus pi over 6, because when you do minus pi over 6, it also has folded into itself. So those would be your limits of integration here for this particular problem. Minus pi over 6 to a positive pi over 6. But then you have to remember the formula for the area under a polar curve. And that formula is 1/2 r squared d theta. So r here is equal to 4 cosine of 3 theta. So this is going to be minus pi over 6 to pi over 6 of 1/2. Okay, 4 squared is 16, and then cosine squared of 3 theta d theta. So that's our 1/2 r squared. Okay, so 16 over 2, that simplifies to an 8. And then we have to go back. We're going to need to use that formula that we mentioned earlier today. The cosine squared of alpha is 1/2 times 1 plus the cosine of the double angle. So this cosine squared of 3 theta then, this is going to be replaced by 8 times 1/2, 1 plus cosine. It has to be twice the angle, so it's going to be 6 theta. Like that. And now we have two terms here that we can get the antiderivative of. This is 8 over 2, so that's a 4. So we have 4 plus 4 times the cosine of 6 theta that we're getting the antiderivative of. Yeah. Is that something seems wrong here with this? Did I mess up on something? 1/2 4 squared, that's an 8. And then I do have the 8 times the 1/2, 4. Okay. Yeah, all right, that's fine. Okay, so this is minus pi over 6 to pi over 6. By the way, did I have to use those limits of minus pi over 6 to pi over 6, or could I have looked at my drawing of my curve and used the different limits of integration? So Nelson, what could I have used?
Just 0 pi over 6.
Yeah, I could have just gotten the area of this upper half, which is 0 to pi over 6, but I'd have to put a 2 in front. I'd have to multiply it by 2. Anyway, maybe I want to just ask this question here. What's the antiderivative of 4 times cosine of 6 theta? Yeah. What? Oh, no. Careful. We have to divide by that 6. 4 over 6. And then we have the sine of 6 theta. And then that's 2/3. All right? And the thing is, okay, let's just play devil's advocate and just say, okay, you thought it was 4 times the sine of 6 theta. Check, if you're not 100% sure that that's right, and of course that can be the problem if you are 100% sure, you take the derivative of this. The derivative of this is going to be 24 cosine of 6 theta. So you're not correct. So that you can always check your antiderivatives that way. All right. Yeah, we don't have time. All right. So then there's the things about those conic sections, our favorite topic, perhaps.
I had a question on 7C.
On 7, the one we just did.
Yeah, when I first did the problem, instead of using negative pi over 6, I used 11 pi over 6, but my integral was going from 11 pi over 6 to 0, and multiply by 2. And I was going to get a negative answer.
Yeah.
Is since it's below the x-axis, is that normal?
Okay. So what happens is actually, 11 pi over 6 to 0, and you got a negative, and I don't know why you would get a negative here, because 11 pi over 6 is equivalent, unless, let's see. It's the fact that you have this here. Yeah, right. Because then when you subtract it off, let's see. Wait a minute, this has did you subtract erase all of that, or what?
No, yeah, that's not all. This is using negative.
Yeah, right.
First time I did it,
First time you did it, so it's all erased. Yeah, because let's see, you would have 11 pi over 6 here, so when you subtracted, this would then be 8 times 11 pi over 6, right, which would give you a negative number. Mm-hmm. Right, that's the reason why, okay, if you're doing an area, yes, you're using the proper limits of integration, and you get a negative answer, just flip it. You know area is going to be positive. Okay. Right? So if you got a negative, just flip it and make it a positive. Okay. Okay. Right. Yeah.
I just redid it on the test to make sure.
Right. Okay. If you have any questions, just send